in a sense, we've looked at a chemical reaction already, right? We've taken these free atoms with an oxidation state of 0 and we formed a molecule from them. So that's a chemical reaction. But let's take a chemical reaction that we normally write as a chemical equation and demonstrate explicitly why the reaction is a redox reaction. And we'll take formaldehyde, CH2O, we'll react that with oxygen, and we know what comes out. CO2 and water are the most thermodynamically stable products, and those indeed are the two products. Now, we know that a redox reaction must involve the movement of electrons. We just explored that explicitly when we analyzed both the oxidation state of free atoms and then what those are within the molecular structure we formed, and we looked at the energy release as a result of that. So it's the movement of electrons, one or more, from one reagent to or toward another. So that means we're going to keep very close watch on exactly what's happening to each one of these atoms. So when you're working a redox reaction, always imagine you're sitting on each one of those hydrogen, carbon, and oxygen atoms, and then you're watching what happens around you when that reaction takes place, because immediately you can see whether electron density is flowing to you or away from you. And if there's a reaction, which there are some, where there's no change in that electron distribution, then it's not a redox reaction. So let's find out whether our formaldehyde plus oxygen reaction is indeed a redox reaction. So we're going to keep track of the electrons assigned to each atom in both the reactants and the products. So let's do this analysis. So we're going to do a counting explicitly in this case for both reactants and products. And to do this, we want to use the rules that we've just worked out for assigning oxidation states. And this is actually very intriguing. So all the atoms in our reaction are nonmetals, so we know exactly where we sit in the assignment of these oxidation numbers. And we have to be very careful of the order that was presented in the table before. So in this case, we don't have fluorine, but we have hydrogen. So we're going to assign the oxidation number to hydrogen first, and then we'll proceed to oxygen second. So step 1, we assign an oxidation state of +1 to each one of those hydrogen atoms, but we have 2 of them. So we sum this together, and that means that we have contributed 2 electrons, 1 from each of the hydrogens. Step 2 is to assign the oxidation state of oxygen. Well, oxygen has -2, so that's interesting. In the formation of formaldehyde, as we saw before, 2 electrons passed into that central carbon from hydrogen, but those same 2 electrons were scarfed up by oxygen at the end of the molecule. All right, so step 1 and step 2 we've completed. Now let's look what happens next. Wow, this is the assignment of oxidation states to each species in this fairly straightforward chemical reaction. So we've done step 1 already. We've pinned down the oxidation state of +1 for each one of those hydrogens, and in step 2 we pinned down the oxidation state for oxygen. So what about step 3? Well, we've already answered this question because we did our detailed analysis of what happens when we take a carbon atom, 2 hydrogen atoms, and an oxygen atom, and we formulate our formaldehyde molecule. And we saw that hydrogen donated 2 electrons, oxygen took up 2 electrons, and that means that carbon was left in its oxidation state of 0. Now, step 4, we want to proceed along our reactants. So oxygen, well, this is easy because the oxygen state of oxygen as a free state is 0. Now let's look at the products of this reaction in step 5. So this is a molecule, all right, it's CO2, but we've already practiced this. There's no fluorine, there's no hydrogen, so we assign the oxygen to an oxidation state of 2. But that immediately solves our step 6 because those electrons are conserved, so we've got a plus 4 on the carbon. So step 7 is to address the hydrogen part of water. Hydrogen has an oxidation state of plus 1, summed together is plus 2, and finally step 8, the oxidation state of oxygen is minus 2. So we've now followed the evolution of the oxidation state for each atom in this chemical reaction. Now we're ready to determine whether we've got an oxidation-reduction reaction. In order to do this, the first thing we want to do is lay out each of the atoms involved in the reactants and the products. The next thing we want to do is to identify the oxidation state for each one of the hydrogen, oxygen, and carbon atoms in this case on the reactant side. So we have an oxidation state of plus 1 for hydrogen. In the case of oxygen, we have 2 oxidation states. We have oxidation state of minus 2 and of 0. And for carbon, we have an oxidation state of 0. On the product side, oxidation state of plus 1. For oxygen, we have oxidation state of minus 2 in one case and minus 2 in the other case. And the oxidation state for carbon is plus 4. So we can see immediately, in fact, the minute we saw that oxygen went from 0 to minus 2, we know we have an oxidation-reduction reaction. And that's substantiated when we looked at carbon, because carbon went from 0 to plus 4. So indeed, we've proved that the reaction of formaldehyde plus oxygen forming CO2 and water is indeed an oxidation-reduction reaction. So what's universal about oxidation-reduction reactions? The first thing is that they provide energy. And they provide energy because this delocalization of electron density, forming that stable molecule, releases energy. What's remarkable is that for more than 1 billion years, life forms were primarily the domain of bacteria. And principally because bacteria evolved to employ redox reactions in very subtle ways in the absence of oxygen, bacteria evolved to become the masters of the game of extracting energy from an array of redox reactions in the absence of oxygen. And so we've looked at cases here where we just take for granted the fact that there's oxygen in the air, and when we combine carbon-hydrogen bonds, the redox reactions take place, producing energy, and that's what sustains biology worldwide.